Hello everyone, today we're going to be looking at usaco-training factorials. Okay, so this problem is pretty simple, so we're given a number, n, and then we're supposed to calculate the most non-zero, or the most right non-zero digit of n factorial. So what means that, for example, you know that 5 factorial would be equal to 1 times 2 times 3 times 4 times 5, which would be equal to 120. And since we're basically getting the rightmost non-zero digit, the answer would be 2 because, as you can see, 0 is and because 0 is 0. And 7 factorial would be 1 times 2 times 3 times 4 times 5 times 6 times 7, which would be 5040. So the most non-zero digit counting from the right would be 4. Okay, so an example would be n equals 7, and our answer would be 4. Alright. So what we can do here is that, notice that n is in the range from, one second. Okay, so n is in the range from 1 to 4,220. And notice that this number, factorial, is way too large, since it would be like very large. So basically brute forcing this number and calculating it would not work. Okay, so now let's try like something else. So notice that for 10, since basically every time, let's just say we have 540. Okay, what we want to do is that we want to divide this by 10 as long as it is divisible by 10. So we would divide this by 10, resulting in 504. And since 504 is not divisible by 10, so then our answer would be the rightmost digit, which would be 4. And now let's notice that 10 is basically equal to 2 times 5. So what we can do is that we can actually break this up into 2's and 5's. So for example, if we have 1 times 2 times 3 times 4 times 5 times 6 and times 7, what we can do here, one second, let me get this over. Okay, so we have our 7 here. So then, when you have our 2, let's have a 2 counter. So let's call this 2 counter. And we also have our 5 counter. Okay. So over here, we see our 2, and we know that this is divisible by 2. So then we divide this by 2, and then that's gone. So then we have 1 over here. 3, you just read over it since it is not divisible by 2 or 5. 4, it is divisible by 2, so then you would tally it up, and then 4 divided by 2 would be equal to 2, and then you divide it by 2 again, which would result in 1. And then 5, you see it's over here. 6, you see that's divisible by 2, and this would result in 3. So then, this makes it a lot more simple, because what we can do next is that we can just keep track of the digits that are currently. So then, what we do is that we start off at 1, okay? So we do 1 times 1 times 3 times 1 times 1 times 3 times 7. So then the key thing is that after you multiply this, let's just say you have basically it would be equal to 3 times 7. This would result in 9 times 7, which would be equal to 63. And notice that 63, or the last digit of 63, is always going to be a non-negative number. And why is this? This is actually because it's because we took out all the factors of 2 and 5. Because we know that it would be, or the last digit would be non-zero if the number is divisible by 10. But if we already removed all the factors of 2 and 5, it would be guaranteed that the rest of the product would end in a digit that is non-negative. So then, basically, when we're multiplying this, for example, we actually only have to keep track of it in a digit. So then, for example, you'd have 3. Well, this is actually a pretty bad example, but basically, now when we're multiplying, let's call this equal to x. So then when we're doing x times y, we would actually result in x times y mod 10. Because all we need to do is to get the last digit, which is the important part. Okay, so for this example, you see that the resulting digit will be equal to 3. But you would say, well, the answer is 4. Well, we actually haven't considered the case over here and over here. So again, you know that 10 is equal to 2 times 5. So then, basically, we remove each 2 if there's a 5 to it. So then we remove 1, 2 for 1, 5, since that's equal to 10. So if you multiply it by 10, it would be, well, it would be like redundant. So then, when we're left with 3 2's, you could just multiply this by 2 times 2 times 2. This would be equal to basically 3 times 8, which would be 24. And then again, this would be guaranteed that you wouldn't have any, or the last digit of this number would be non-negative. So then, again, we just take this mod 10, and instead of having this, or instead of this, your answer, since you are modding it by 10, this would be equal to 4. Okay, so that's basically it. And this would actually run pretty quick because every time we're dividing it by 2, or if we're dividing it by 5 here, this would actually take logarithm time, since we're actually dividing it by at most log x, whatever the number is. So this would actually run pretty quick as well. Okay, so let's get to coding, and this is Factorials. Alright, so let's include, again, stdio.h. Okay, so we have our main function. So we're given a number n. Okay, so we're going to have our d, which is the current digit, and, whoops, I actually spelled this wrong. Scanf. Okay, so d is going to be the last digit. So we can have it by 1 by default. And then we can also have the number of 2's we have, and the number of 5's we have. So then we loop through I from 2 to n. Okay, so then we're going to try to basically factor or divide this by all the 2's or 5's. So what we can do is that we can have a duplicate of I, since we actually don't want to modify this. Since if we modify it, then this would basically repeat. So we can have basically I apostrophe. Okay, so then we're going to do this while I is divisible by 2. We're going to divide I by 2, and we're going to increment the number of 2's. And again, while I is divisible by 5, we're going to divide it by 5, and we're going to increment the numbers of 5's. Let's actually call this 2's. Okay. So now we're ensured that when we multiply our resulting I and d, the last digit would remain non-negative. So then, we would update our d equals to our d times I mod 10, and this should actually be I. Okay. So at the end, for example, in our case, we will result in a 3. So then we would actually remove all the 2's, or remove all the 5's and the 2's, because as I said before, 10 it would be equal to 2 times 5, so we want to remove all the occurrences of 5's and the 2's. So then we can do 2's will be equal to 2's minus the inverse 5's. Okay, so now we're just going to multiply d, which is a digit, by d2's. So then d would be equal to d times 2 mod 10. Okay, so then our answer would be D. Actually, there's nothing there. Alright. Okay, so this is the usaco-training Factorials. Okay, so let's run main. Alright, so it's pretty simple. The sample is 7, so we have 7 here. 4 which is correct, so let's actually submit this. So we can use free open. We're going to read from fact4.in, and we're going to write to fact4.out. Alright, so okay, let me just enter the information. This is fact4. There's no C++1. At least I'm pretty sure there isn't. Alright, so let me select the file. Okay, so this is usaco-training, and this is Factorials. Okay, so main. Let me submit it. Ooh, okay. Interesting. So it used, okay, that's weird. Okay, so let's actually copy that back to our program, and let's actually try running that. Oh, okay, so I kind of see. Okay, so I actually did a pretty big typo, so this should be stdn, meaning that we're reading from fact4.n, we're not writing. So that should be correct, and let me choose this again. Alright. Okay, so it is okay, and it's correct, or AC'd. So if you have any questions, feel free to leave them in the comment section below. So bye.